Hello, welcome to my pipeline integrity video series, Things That Make Me Go. This is part 7 in the series. Hopefully you've seen some of the earlier parts, 1 to 6, but if you haven't, I hope that you'll still find some interesting features in this particular video. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. So today we're going to look at ASME modified B31G length and depth effects. If you're watching this video, I'm assuming that you're somehow involved in the pipeline integrity industry, and you're probably familiar with this model because it's used for corrosion assessments. The model has been around for many, many years, and it's written into code in Canada, it's written into code in the United States, and I'm guessing some version of it in some way, shape, or form is probably written into code in various other parts of the world. If you've seen some of my other videos, you realize that I'm really not at all a fan of the basic mathematics underlying modified B31G. The mathematics were developed by the Battelle Institute back in the late 1960s and early 1970s, and I've got a few mathematical and theoretical issues with the way that model came together. So what I'm going to do here is I'm going to show you that there are some length and depth effects that you might need to be aware of if you're involved in this type of work. So here's our modified B31G equation. Hopefully some of you have seen this before. We have a remaining strength on the left-hand side, which is defined as the predicted strength divided by the flow strength. And on the right-hand side, we have this monster fraction here, 1 minus 0.85 times d over t, where d over t is the corrosion flaw depth ratio with respect to wall thickness. And all of that is on top of 1 minus 0.85 over m times that same d over t. And if you've seen this equation before, you know that the m is the Foley's factor. The Foley's factor is a strong function of length. For those of you that need a bit of a history lesson, the Foley's factor was originally derived looking at through-wall cracks. And the question was, would a through-wall crack that was short get longer and rupture a pipe? So the Foley's factor is very much focused on length and extension of a crack. This is not actually particularly useful for looking at surface flaws. With surface flaws, we're worried about a shallow crack getting deeper. So we're looking at an entirely different dimension. And if you've seen my previous videos, you'll see that because of this, this equation is mathematically focused in the wrong direction. With that Foley's factor in there, you're focusing the mathematics on length when you really kind of sort of should be focusing the mathematics on depth. And that has a couple of really interesting effects. Makes all the mathematics go wonky, as I'll show you. So here I'm going to be looking at two primary data sets. One I'll call the Cronin data, one I'll call the Battelle data. It's a grand total of 85 data sets. In the case of the Cronin data, I have several profiles, about 20 to 25 profiles. With the Battelle data, I don't have the profile, so I can't do any of the more advanced calculations. I'm not going to be doing those today. All of these data points, basically, I have the diameter, the wall thickness, the yield strength of the pipe, I've got the length and depth of the corrosion flaw, and I've got the real-life hydrotest failure pressure. So what I can do is I can use that modified B31G equation to come up with a prediction as to what the failure pressure of that pipe is going to be, and then I can compare it to the actual true failure pressure. So that's what I'm going to do with a simple validation exercise. So here I've got those 85 data points. I've sort of clustered them all together, both data sets together, because they seem to behave in a fairly common fashion. On the y-axis, I've got my predicted failure strength, and I've done that as a fraction of yield. And then on the x-axis, I've got the actual true measured failure strength, again, normalized by the yield strength. So what you'll see there is our data tends to be lower than the unity line, lower than the diagonal line going through the middle of the plot, indicating that on average, modified B31G is relatively speaking, a conservative model. We do see a few data points that are above that diagonal line indicating non-conservative and potentially unsafe predictions, but the great majority of them are below the line, and these represent conservative predictions, though some of them are conservative enough that we would perhaps be spending an awful lot of money if we were to dig them all up as pipeline operators. Now, you'll see that the trend line I've put through there is 0.82x, and if we think backwards, that means that we've got about a 25% over conservatism built into this modified B31G model. Now that's going to make a lot of people feel pretty good. They're going to think to themselves, well, 25% conservatism is going to make us feel all very safe, and that's all good. But as I mentioned before in some of my earlier videos, I've got some serious concerns with the theory and the math behind this equation. So, let's see if I can think of a way to figure out under what conditions this model might be too conservative, and under what conditions this model might be not conservative enough. If you've seen my video, Things That Make Me Go, Part 1, I basically demonstrated that if you take this equation and you turn it inside out, it will demonstrate that longer flaws will tend to be more conservative, and shorter flaws will tend to be more accurate. So what I've decided to do here is take all of my data points and group them by the flaw length, and then color code them and plot them over again, just like I did, just to see if there's any pattern. Turns out that works out fairly well. If I take all the shortest of the flaws that I have in my data set, which I've defined here as length divided by radius of less than 1/4, and I plot those all in red, those all turn out to be, relatively speaking, fairly accurate predictions by modified B31G. If I go for some slightly longer flaws, and in this case they're length over radius somewhere between 1/4 and 1/2, I find that I've actually, on average, increased the conservatism there. That's shown by the yellow data points. If I go for the longer flaws, and here I'm defining the longer flaws as equal to or greater than 1/2 in terms of length over radius, I'll find that on average, all of those data points are much more conservative. So that's really a very interesting thing to find. When I plot these all up, it looks like I've got a big set of traffic lights or something like that. All of my shorter flaws are on the top, all of my medium flaws are in the middle, and all of my longer flaws are on the bottom on average. Now, you'll see that there is a little bit of a mix and match between some of those data points. It's not quite as clean and clear as you might want it to be, or you might hope to be in order to make better predictions. Now, to explain why there's a whole lot of mix and match, we can do exactly the same sort of exercise, but rather than looking at different lengths, we can actually take all these data points and we can group them by depth. In this case, what I decided to do was to take all the data and split it up into 20% flaw depth ratios. Let's see how that plays out. So here I find a similar pattern as well. You'll see that for all the shallow flaws, which I've shown with a red circle, they tend to be at the top of the plot. And as I work my way from the shallowest to the deepest of the flaws, I go from red to orange to yellow to green to blue. And surprise, surprise, I find that my trend lines also go from top to bottom in this particular plot. So what that's meaning is, as I go from a shallower flaw, where I'm relatively speaking fairly accurate in my modified B31G prediction, as I go to the deeper flaws, I'm actually getting increasingly conservative. Now, increasingly conservative might mean that I'm safer, but it might also mean that I'm digging up a lot of stuff that I really don't need to dig up as a pipeline operator. You'll see that there's a fairly clear pattern here in terms of the trend lines and the averages. Now, if you think about it, what I've done is I've done two separate validations, one where I'm grouping by length and one where I'm grouping by depth. Both of those seem to show a pattern, though obviously there is some overlap in the various data points because each one of these flaws will have a different combination of length and depth, and who knows how the morphology changes from flaw to flaw. But I find that to be a very, very interesting pattern there. We actually have a nice rainbow almost of data points there. Very interesting to think about. This has, I'll say, some quite significant ramifications on how pipelines are being managed these days in terms of corrosion assessments. We see from these two plots that if we have shallower and shorter flaws, we're going to tend to have fairly accurate predictions. But as we go to longer and deeper flaws, we become increasingly conservative. And what makes that a really interesting thing is it means that the pipeline operators are going to get caught in kind of a catch-22 situation, where the longer and the deeper a corrosion flaw becomes, the more and more likely they are to put it on their dig and repair list because it's got a low failure pressure. But at the same time, the longer and the deeper they get, the more likely it is that modified B31G is giving them a overly conservative prediction. So it kind of puts the pipeline operators into a catch-22 situation, which I demonstrated before in some of the other videos. If you're as boring as me and you're interested in this kind of stuff, you might want to see some of my my other videos, pipeline integrity things that make me go parts 1 to 6. And that's basically a video series where I critique the NG18 based assessments for corrosion and for cracking. And as I mentioned earlier, the NG18 equations, they essentially mathematically focus the failure pressure predictions on the flaw length rather than the flaw depth. And what we've seen in these two videos, these two validation plots, is that the mathematics behind that model essentially skews everything in terms of length and depth. It means that the model is mathematically wonky as its basis, and we need to be aware of that when we're doing risk assessments. I also have my own model called the gamma exponent model, which I've developed, which tries to clean up the problems associated with ASME B31G. And if you look at that series, you'll find that I've got a new model that looks at all sorts of different flaw types, axial and circumferential cracks, SCC, corrosion, through-wall crack assessment, leak rupture boundaries, all sorts of stuff. And you'll see from my validation efforts that the gamma exponent model actually cleans up some of the problems that I've discussed today. So please check those out. If you're more interested in actual real work that's been published by real societies rather than just looking at YouTube videos, you can find I have a NACE paper from a little while back. Take a look at that. I have an ASME pressure vessels and piping conference paper, which looks specifically at axial crack assessment. And for those of you that are really nerdy and interested in how I've derived my gamma exponent model, take a look at the ASME Journal of Pressure Vessel Technology paper from a little while back. That's it from me for now. Thank you for your attention. I hope I've given you something to think about, and that the way I've plotted this data kind of makes sense to you. I was quite surprised when I plotted the data, and I found that you actually do get, such an interesting pattern in both the length and the depth, despite the fact that you've got various combinations and permutations of lengths and depths in your data sets. The effect is still strong enough that you can see a pattern in both length and depth variables. It's got very significant ramifications, I believe, on various pipeline operators' integrity programs. Fixing this problem using the GEM model can save certain people tens or possibly hundreds of millions of dollars. But that's on them to figure out. Give me a shout through LinkedIn if you have any questions. Thanks very much.